Yes, sir.
Yes, sir, you're audible.
Okay, thanks. Okay, so in this session, mostly we'll revise the concepts of week 5 and 6. Okay. Okay, so I'll start now. Okay, so let me start with the concept of week 5. So yeah, so basically week 5 starts with the definition of one function. Okay. Okay, can one of you tell me what is the definition of one function?
Sir, for fx2 equal to fx1, fx should be equal to fx.
One input and one output on this.
Anyone else who wants to say?
May I, sir?
Yes, please, obviously.
If f of x1 is equal to f of x2, then x1 is equal to x2.
Correct. Yeah, correct. So suppose we have a map. Let's say we have a map from A to B, right? So that means this is my domain, right? And this is the codomain of the function. Suppose I have a map from A to B, then I say that my function is 1, or in different terminology for 1 is injective. Okay, so I say f is injective or 1 if for all x1 comma x2 in my domain. Okay, so for all x1 and x2 in my domain, if f of x1 is equals to f of x2, then this should imply that x1 is equals to x2. And there is one other equivalent definition of this 1 function. Can one of you tell me what is the other equivalent definition of 1 function?
Injective function.
Anyone?
Sir,
Line test, sir. Line test.
Sorry?
Are you asking about the vertical and horizontal?
No. That is, I'm asking the definition of some other equivalent definition of 1 function.
so we can say that f of x1 is not equal to f of x2, then x1 is not equal to x2.
Yeah, so you have said like
Just reverse of this.
yes, correct. Yeah, you are correct. So you have said the reverse thing. So equivalently, what I can say, I can say that if x1,
sir, can we say that if x1 is equal to x2, if x1 is equal to fx2?
that is true for every function. Then what is special about 1 function?
Okay.
equivalently, what I can say, if x1 is not equal to x2, then this should implies that f of x1 is not equal to f of x2. So there are, as you can see, there are, so both the definition are equivalent. So you can use appropriately, like whatever is required in your proof, you can use that to show a function is 1, 1. Okay, so let's consider few examples. So let's say you consider this map. So you consider this map. It's a map from the set of all integers to the set of all integers. And what is the definition of this map? F takes n to 2n plus 1. So any idea how to check whether this map is, so what we want to check, whether this map is injective or not, right?
Yes, sir. It is a linear function.
Yeah, so how we can check that?
We will do like we consider like n as a n1, and then we'll do 2n1 plus 1 is equal to 2n2 plus 1, and then we try to check if n1 is equal to n2.
Correct,
Yes,
absolutely
yes,
correct.
sir.
Yeah. So basically what we are, so in this case, what we are applying this. So whatever C said, basically C is applying this first rule. Okay. So suppose you consider two numbers in your domain, right? So this is inside your domain, and let's say f of n1 is equals to f of n2, then what you can get from the definition, this is precisely 2n1 plus 1, which is same as 2n2 plus 2, right? Sorry, not 2n1 plus 1. And I can easily cancel this 1 and 1. So from there, what I can get, 2n1 is equals to 2n2. And from here, I can get that n1 is equals to n2. So what basically we proved? We proved that if we proved that if f of x1 or here f of n1 is equals to f of n2, then this implies n1 is equals to n2. So this is an example of an injective function, right?
Yes, sir.
So suppose next you consider this map. Okay, you consider another one from the same domain to codomain, and here the definition of map is slightly different. And what is this map? F of n is 3n square plus 2. So what about this map? Whether this map is injective?
No, sir.
It is a quadratic function, so it will not be a
Yes.
1, 1 function.
Yeah, tell me why. Like, see, you are basically saying you need to show that this is not injective.
So we will show it like 3n1 square plus 2 is equal to 3n2 square plus 2. If they are not equal, then the function is not 1, 1. If they are equal, then the function is 1, 1.
Anyone else?
Sir, this is not one.
Yeah, that is fine. Like, see, this is not 1, 1. I'm asking why.
Sir, we
Sir,
will
if we draw the graph, we get to know that it is a quadratic function. So it's a upward facing parabola. And if we draw
No,
a horizontal line, it cuts on two
is
ends.
not parabola. This, see, the problem is the problem is here the domain is not R, it's integer, right? When you
Oh,
are
okay.
when you are drawing a parabola, so you are drawing over a real line, not over integer. Okay.
Yes, sir. So half the okay.
Sir, we will
Okay.
take minus n and plus n.
Correct. Yeah. Correct. So as someone already said, if you take f of n, okay, this is 3n square plus 2, and you will get the same value if you consider the value of f of minus n as well. Okay, so in particular, if I take f of 1, then it will give me 5, right? And if I consider f of minus 1, the same, I will get the same value, right? So what is the problem here? Now I have, so this is my domain and this is my codomain. So I have two things in my domain, 1 and minus 1, and they basically go to the same quantity in my codomain. So that's why my map is not 1 function. Correct? Any doubt till now?
No.
Okay,
No,
fine.
sir.
Okay, so similarly, let's say, okay, so maybe these are, I'm taking very easy example. Let's say again, let's say you consider this map. Now you consider from R to R, where f of x is x square. So what about this function?
Not 1.
Not 1, right? The same logic, same argument will show you that this map is not 1. And again, you take the same domain and codomain, R to R. And here x goes to modulus of x. What about this map?
This is also not 1.
Because again, the same logic, 1 goes to 1, minus
Yeah.
1 goes to also 1,
1.
right? So these are the standard example, like where you can show that this function is, these are the function which are not 1. Now, if I consider, let's say this function.
Excuse me, sir.
Yes.
Sir, on what basis we decide like what procedure we should follow? Like, sir, putting 1 and minus 1, or x1 and then x2 by putting two different values, x1 and x2. So
See,
in the first example, we applied that procedure.
See, because in the first example, so the thing is, in the first example, actually, I wanted to show that this function is injective. Okay. So when I can say that the function is injective, okay, if my function satisfy the condition for all x1 and x2 inside my domain, right? For all x1 and x2, okay.
Mm-hmm.
So that's why I actually started with arbitrary n1 and n2, right?
Right.
But when I want to prove that my function is not injective, okay, then what I have to show?
So in case we need to tell whether it is injective or not.
Yeah.
So what we are supposed to do?
Then first, the thing is you have to guess, okay, what is your feeling, okay, whether this function is injective or not. Okay. So first you have to make a guess, okay. So whether this function is injective, okay. If you feel the function is injective, okay, then you have to start with this one, okay, because you have to prove, right? You have to prove that this condition holds for all x1 and x2, right? So see, if you have to show that condition is true for all x1 and x2, then you cannot start by putting arbitrary value, right? Because there are infinitely many choice of x1 and x2, right? If my domain is Z, there are infinitely many. For example, x1 can be 1, x2 can be 3, then this can be 2, 3, 3, 3, 4, 3. So there are infinitely many choices. So I cannot check for all the values. Okay. So that's why I have to start with arbitrary n1 and n2, right?
Right.
So if I start with arbitrary n1 and n2, then basically this will include all the possible n1 and n2, right?
Right.
But when I'm trying to prove that the function is injective, but when I'm trying to show that the function is not injective, then basically what I have to show? I have to show that this condition is not true, right? This is not true. That means I have to basically see what basically means by this is not true. Okay, this statement is saying this condition should hold for all possible x1 and x2, right? I can show that this condition is not true if I can provide you two x1 and x2 for which this condition doesn't hold. Right? That is what I'm doing when I'm trying to prove that this function is not injective. I'm basically I'm providing you one one possible pair x1 and x2 for which this condition doesn't hold. So the first thing is you have to guess whether
Yes.
this
Okay.
is an injective function or not. Then
Okay.
accordingly you have to see if you want to show that this is not injective, then you have to provide a counter example. That is what we are doing here. Okay.
Okay.
And when you want to show that this function is injective, then you have to prove it. Okay.
Okay. Okay. Rick. Thank you, sir.
Okay, so now again, maybe let's take the last example. Suppose you consider this map from R to R, not R to R, let's say R minus 0, where x goes to 1 by x. What about this map?
Yeah, 1 function.
Injective, sir.
This is
1
1, right? This is injective. How I can prove it? How I can prove it?
taking different input values.
Yeah, so it's clear, right? If suppose you consider the second, if x1 is not equal to x2, right? That means 1 by x1 is also not equal to,
1 by x2.
that means f of x1 is not equal to f of x2, right? So this
Yes,
is one. So in this way, you can show that this function is injective, right? And there is one other graphical method through which you can say that the function is injective or not. And what is that method?
Horizontal line.
The horizontal line test.
Correct. Right. So what basically it says, if you consider this graph, let's say you have a graph like this. So if I draw a horizontal line, okay, if I draw a horizontal line, then I can easily see that. So here I have x1 and here I have x2, and as you can see, this horizontal actually line crosses this this horizontal line cuts the graph at 2 points, right? So that means I have x1 and x2 for which f of x1 is same as
f of x2.
F of x2. So by using this test, I can easily say that this whatever function this graph represent, that function is not injective. Okay. So for example, if I have a graph like this, let's say I have a graph like this. Okay. So no matter what horizontal line I take, doesn't matter. Okay. It always crosses the graph at exactly 1 point. Okay. So in that case, what I can say that whatever function this graph represent, that function is
1
injective or 1. Yeah. Okay, clear? Any doubt from 1
No.
Okay. Any specific example you want me to consider?
Is there only mod x and square functions are not one-to-one, else others are always one-to-one? Is that?
No, for example, if you consider the parabola, right?
Parabola is the graph of a square function like quadratic.
Yeah, quadratic. Even if you take, let's say, you take this one. So you consider this is not.
Sir, after simplifying this, it will also become quadratic, x common, and then.
Sorry?
after simplifying this equation, after taking x common, that will also become quadratic.
Okay, see, no, that is not become quadratic. You will get a quadratic factor. Don't tell that will become a quadratic. This is a cubic.
Okay.
Okay. So again, still, if you are not convinced, you take sine function, right?
Okay, sine function, that will not
See,
satisfy.
there
Okay.
are lot of function which are not one. Okay, so there are a huge number of functions which are not one. Okay,
Okay, sir.
you consider this function log of x square. Okay, do you think this
Okay,
is one?
no, sir.
Yeah, so
Mm.
so you can create lot of functions which are not one. So nothing special about, yeah. So of course, this modulus and square, they are not one, but again, you can create a lot of more functions which are not one.
Sir, I want to ask one thing. Sir,
Mhm.
just now you wrote log of x square. Sir, I wanted to ask, like, why we don't call it as quadratic when the equation is inside the log?
No, see, again, see the thing is, what is the definition of quadratic? What do you mean by quadratic function?
Sir, it will give us two roots.
No,
Maximum.
It's in the
Max
form of
power 2.
ax square plus bx plus c, where a is not equal to 0.
See, this is precisely, if you can write a function in this form, okay, so in that case, you call a function to be a quadratic function, right? So
Yes, sir.
log x actually, okay, so again, see, the log x has a power expansion. Okay, so you can't actually write log x in this form. You can't write this function in this form. Okay.
But
That-
sir, if we have instead of x, if we have equation inside, we cannot call it either, like we cannot call it.
No.
Yeah.
So that is the problem. That's why you can't say that log x actually what, in some sense this is a infinite series. Okay, if you try to write down the again, you need differentiability to talk about the log series. Okay, so if you try to write down the, again, like, see, I'm writing something. So the expansion of log is probably this one, n wants to infinity minus 1 power n minus 1 x minus 1 by n. So this is a power series. Okay, you can't write this log x in some quadratic, using some quadratic polynomial. Okay, so that's why this log x is not log, it doesn't matter x or you put x square, this will never become a quadratic function. Okay,
Sir, what is this expansion
you expand it, right? So again, this is called Taylor series expansion.
We haven't studied this.
Yeah, that is what.
Yeah.
Okay, so I don't want to go there. Okay, so but yeah, keep in mind that this log x square is not quadratic. Okay, the one and only reason is you can't write log x square in this. Okay.
Okay, sir.
Yeah.
Okay.
Sir, is there any way, like for 1-to-1, we use the formula to derive, right? Whether the function is 1-to-1 or not. So is there anything for onto also? Because for onto, we always do hit and trial.
Yeah,
Right?
onto is always difficult compared to 1-1. Okay, because there is no such method like as you said.
Okay.
So and the problem with onto is also, there is one more problem with onto. So onto actually depends on domain as well as codomain, right? Whereas your 1-1 only depends on the domain. Okay, so when you are checking whether a function is 1-1, okay, the only thing that matters is basically what is the domain of the function. Okay, but when you are checking the onto-ness of a function, it basically matters from where to where you are defined. Okay, it matters what is the domain as well as codomain. Okay, so it's so checking onto-ness is always difficult than checking 1-1-ness. Okay, because there is no, yeah.
Sir, can you elaborate it?
No,
how-
because see, the thing is, because ontoness is not there, at least in week 5. Okay, so that's why I don't want to go there. Okay, so if you ask me some regular session, then probably I can spend more time. Okay, this is more or less a revision session.
Okay, sir.
This okay, so I'm actually doing it for the exam point of view. Okay, so yeah, so okay, till now everything is fine.
Yes, sir.
Okay.
Yes,
Yes.
sir.
Yes, sir.
Okay, so next, let's go to even and odd function, right? So, anyone, what is the definition of even function?
F of -6 is equal to f of x.
Correct. So if I have a map from A to B, if my map satisfies this condition, for all x, suppose I have a map from A to B, if they satisfy this condition for all A in B, then you say that my function is even function, right? So what basically it's saying? So graphically what it's saying? Suppose I have a function. Okay, what actually it's saying? The value of the function at x, right, is same as the value of the function at minus x, right? So in some sense, what it's saying, it's if I draw the graph, okay, if I draw the graph, then the function is symmetry about y-axis, right? So for example, if I consider the graph of x square, let's say this is the graph of, let's say, this f of x equal to x square, right? So if you take f of x equal to x square, then as you can see, f of minus x is minus of x square, which is again x square, which is same as f of x, right? So this is a even function, right? So any other example of even function that you know?
Mod x.
Correct. So if you consider this one, again, this is a even function, and from, if you know the graph also, from there itself you can say that this is a even function, because if you draw the graph of mod x, then you can easily see that this is symmetry about y-axis, right? This is clearly symmetry about y-axis, and that's why this is also a even function. Okay, and similarly, any other example, any other trigonometry function that you know? This is
Cosine.
Cos x, sir.
Cos
Cos x.
x, cos x.
cos x, right? So this is a even function. So if you draw the graph, then at 0 it's 1, right?
Yeah.
So it will go like this. So this is an example of a even function, right? So there are a lot of examples of even function, and yeah. So the next thing is odd function, right? What is the definition of odd function?
F of minus
F of minus x is equal to minus f of x.
Correct. F of minus x is equals to minus of f of x. Okay. So yeah. So again, sir, I made a mistake. Right. So what actually it's saying geometrically? Suppose this is my x, right?
Parallel to x-axis.
Not
Sir,
parallel.
sir, it will have a symmetry along
Symmetry.
x-axis.
Yeah, symmetry.
About origin.
Not x axis.
Symmetry against
About
the origin.
Origin,
The
origin, yes, origin.
Right, right. So
Like sin x.
yes. So suppose this is x and this is f of x, then at minus x, what I will get? I will get completely. So if this distance is f of x, then I will get the negative of that. So I will get this one. So this is my f of minus x. And how I am getting? By using this property, because it's saying f of minus s is nothing but minus of f of x. So if I draw the graph of a odd function, this is always symmetry about origin. Okay. Right. So any examples of again, like the sine function is a example. So if I consider f of x equal to sine x, then if you draw the graph again, like it's more or less similar to not similar. Okay, if you know the graph of cos x, then you can easily draw the graph of sine x. So this is an example of an odd function. So apart from sine x, any
X
any-
cube.
Only
sir.
x, sir.
x cube, correct. X cube is a odd function. So if I consider f of x equal to x cube, then you can easily prove that f of minus x is minus of x cube, which is nothing but x cube minus, and this is nothing but minus of f of x. Okay, so this is an example of a odd function, right? So now if I consider, suppose let's say I consider this example, let's say f of x equal to 3x square minus 4. So what kind of function is this?
Even function.
Parabolic.
This is a
Even function.
even function.
Even function.
Correct. And what about this one? Let's say f of x equal to x cube minus x square.
This is
Odd function.
No.
This is a odd function.
Neither.
So if I consider f of minus x, then what I will get? Minus of x cube minus of x square, right? And this is nothing but minus of x cube minus of x square, right? So do you think this is whether this is same as f of x?
No.
And do you think this is same as minus of f of x?
No.
Right? So this is neither even nor odd, right? This is neither even. So you can have some function which is neither even nor odd. Okay. Okay, and this is an example of that. Okay, so again, let me ask, suppose a graph is given, right? Suppose a graph is given. Suppose a graph is given, let's say like this. And some part of the graph is given, and it's saying that this function is even function. Okay. Then how you can easily draw the graph of the full function, right? Because what you know, a even function is symmetry over
Y-axis.
correct. So once you know one part of the even function, you can easily draw the other part of the even function, right? So,
Right.
so that is the advantage of even as well as even function or odd function. Okay. So it doesn't matter. Similarly, you can draw if some part of one side of even odd function, then you can easily extend the function into the other part, because you know that if a function is even, then it is symmetry about y-axis. If the function is odd, then it is symmetry about origin.
Origin.
Yes. Okay. So the next point is increasing function and decreasing function. Anyone? What is the definition of increasing function?
May I, sir?
Yes.
If f of x1 is greater than f of x2, then x1 should be greater than x2.
You are saying
F of x1 is greater than f of x2, then x1 should be greater than x2.
yes. Again, it's better to write in the other way. So if x1 is greater than x2, then this should imply that what?
F of
F
x1
of
is
what?
greater than f of x2.
Is not greater than, it's greater than or equal to f of x2. Okay. See, you can remove this sign. Okay. If you will use this instead of increasing or decreasing, if you use strictly increasing and strictly decreasing, in that case, you can use this strict inequality. Okay. Otherwise, it's greater than or equal to. Okay.
Okay, sir.
Yeah. And similarly, what is the definition of decreasing function?
If x1 is greater than x2, then f of x1 smaller than f of x2.
Again, this should hold for all x1, x2 inside the domain, right? So, any example of increasing function?
Your identity function is
Sir,
increasing.
here you have written equal to also, greater than or equal to.
Yes.
So in case of a constant function, then also it will be applicable.
Correct. Increasing function, even constant function is also a increasing function. See,
increasing or decreasing, sir?
Both. See, that is the definition of increasing. Okay. If I, instead of this, if I use this one, strictly increasing, okay, then I have to remove this sign. Okay, strictly increasing or strictly decreasing. In that case, I can remove this sign. Okay. Otherwise, if simply I'm saying this is the increasing function and decreasing function, that means I have to keep this sign greater than or equal. Okay. So as someone already said, if I consider the identity functions, let's say not identity, even the constant function. Let's say f of x equal to 1, right? This is a constant function. Okay. So this is a increasing function. Right? Because it doesn't matter what the value of x and x1 and x2, then I'll always get this equality sign. Okay. And similarly, also you can say that this constant function is a decreasing function. Okay. Right? So, but as you can see, this constant function is not strictly increasing function, right? This is neither strictly increasing, not strictly decreasing, right? Because
Yes,
if I remove this less than or equal to sign, so if I replace this one with strictly greater than and strictly less than sign, then this constant function is not a strictly increasing or strictly decreasing function. So any example of strictly increasing and decreasing function?
F of x is equal to x plus 1.
Yes, correct. So if I consider this example, f of x equal to x plus 1, then this is a strictly increasing function, right? Because what basically it's saying, if x1 is greater than x2, right? That means
F of x
x1 plus 1 is also greater than
x plus x2 plus 1. Right, sir.
right. So this is an example of a strictly increasing function. And any other example that actually that you
X
have.
cube, sir.
Sir,
Sir, give
exponential
any
function.
example which is gives us equal
So
f of x1 equal to f of x2, like only increasing, not strictly.
no, so again, like, see, mostly actually, yeah. So I'm mostly concerned about this strictly increasing. Okay. So instead of increasing and decreasing, let's consider this strictly increasing.
Okay, sir.
Sir, exponential function when a is greater than 1.
Correct. So yeah. So I basically wanted to know this answer. Okay. So if you consider this exponential function, let's say 2 power x. Yeah, so let me write exponential function if a is greater than 1, right? So for example, if I consider this function f of x equal to 2 power x, then it's clear, right? If I take x1 is, if my x1 is strictly greater than x2, then 2 power x1 is also strictly greater than 2 power x2. So, and from here, from the graph also, you can easily say that your function is strictly increasing, right? So
Yes, sir.
it's basically going above. So if you pick any x1 and any x2, so as you can see here, okay, let me change the sign. So as you can see, if your x1 is greater than x2, then this is your f of x1, right? And this is your f of x2. And from the graph, it's clear that this length is always greater than this length. Okay. So this is an example of a strictly increasing function, right? So again, like you can replace 2 with any number which is greater than 1. And what is the advantage of this strictly increasing and strictly decreasing function? They are what? They belong
1-to-1 function.
1-to-1 function,
correct.
sir.
So they belongs to this category of 1-to-1 function. Okay, so that is that is the main one and only reason that we are studying, at least in this course, about this strictly increasing and strictly decreasing function. Okay, it doesn't matter. So if it is strictly increasing or strictly decreasing, both are 1-1.
If we will not use strictly, then it will be not 1-to-1, right, sir?
No. So what actually I'm saying, if a function is strictly increasing and strictly decreasing, okay, then they are 1-1 function. Okay, that is what I am saying. Okay, I'm not saying that all 1-1 function should satisfy one of them. Okay, right. See, I'm not saying all 1-1 function will satisfy the condition. What basically I'm saying, if a function is strictly increasing, so A implies B. That is what I'm saying. If a function is either strictly increasing or decreasing, then that function is 1.
Yeah, I get it, sir.
Okay.
Excuse me, sir.
Yes.
Yes, sir. Can I identify increasing function and decreasing function by derivative rule?
If you can, if you want, you can, like, yeah. So if the derivative
Yes, sir.
is
How-
greater than 0, then you can say that this function is increasing.
Yes.
And
Okay.
if derivative is less than 0, then you can say that the function is decreasing.
Yes, sir. Here I confused that, sir. X1 and X2, sir. What does this mean, sir?
Sorry?
Sir, X1 and X2, sir. What does this mean, sir?
This is a point in your domain, right?
Okay, sir.
See what basically it's saying. Okay, let's go back to the definition. What basically it's saying. Okay, so if I pick a number in my domain, okay, they both belongs to the domain, right?
Yes, sir.
If I pick a number in the domain, which is x1 and 2, sorry, if I pick two numbers in the domain, x1 and x2, and with one more condition that x1 is greater than x2, right? And then if I consider their values, okay, if I consider their values, f of x1 and f of x2, then for strictly increasing function, I can say that f of x1 is always greater than f of x2. See what basically it's saying. So if you try to draw the graph, okay, so if you try to draw the graph, let's say the graph of strictly increasing function. See, if you move along the x-axis from minus infinity to infinity, right?
Yes.
In this direction, then the values are increasing, right?
Yes, sir.
The values are increasing, right? You are actually going from some lower values to some higher values, right?
Yes, yes,
So according to the strictly increased function, so when you are going from lower values to higher values, the value of the function will also increase, right? So for example, if I consider this one, okay, let's say this one, if I consider this graph, okay, so when you are going from negative to positive direction, right, you can say the value of the function is also increasing, right?
yes, sir.
So that's why this is an increasing function, strictly increasing function. It's actually the value is increasing strictly. Okay, so that's why this is a strictly increasing function, right? So but for example, if you consider this graph, right? If you consider this graph,
Both increasing and decreasing.
yeah. So
First decreasing, then increasing.
No, this is not neither increasing nor decreasing.
No, first decreasing and then increasing.
No, that is okay. That is correct. But this is again, that is also that is what I am saying. It's neither increasing or decreasing, right? See, first increasing, then increasing basically means it's neither increasing nor decreasing, right?
Depends
See,
on the interval.
Yes, sir.
yeah, if you restrict the interval, see, if you restrict the interval up to here, okay, if you take this part, okay, then clearly it's increasing, right? If you consider 0 to infinity, right, it's
Yes.
increasing, right? And if you consider minus infinity to 0, then it's decreasing, okay? But if you consider this function as a whole, minus infinity to infinity, it's neither increasing nor decreasing, right? Because as you have already said, so when you are actually coming from minus infinity to towards 0, right, then the value of the function is what? It's decreasing, right?
Yes.
And when you are going from 0 to infinity, then the value of the function is increasing. So as a whole, it's not behaving uniformly. Okay, so that's why it's neither increasing nor decreasing. Okay, so but again, like if I consider, let's say this example,
Sir,
let's say this example. What about this function?
sir, this is
Always decreasing.
Strictly decreasing.
Yeah, strictly decreasing. As you can see,
Yes.
if you are if you're increasing the value in the domain, okay, then the value of the function is actually coming down. Okay, it's coming down straightly. So that's why this is a graph of a straightly in decreasing function. And once you know this is straightly decreasing, then you can say that this is a 1-1 function. Okay. Okay, any doubt till now?
Sir, x cube will be strictly increasing or not?
X cube.
Strictly increasing.
What is your thought?
Sir, actually, I am thinking because at origin, it flattens x cube or x5 or greater degree functions. Means if we take x5 at origin, it flattens, means it goes parallel to x-axis.
0 to infinity, it will increase.
Just a minute. Let me draw the graph of x cube.
Sir, take x cube or high
No, let me
degree.
take x cube. So what is the graph basically?
Sir, here at origin, it becomes parallel to x-axis.
It's not parallel. See, the thing is, if you zoom it, then you can see it. Okay, so this is a big picture. Okay, so this is actually increasing. You can simply prove it, right? See, if x1, so if you go and
sir, theoretically, I can prove
yeah,
it,
so
yeah.
the problem is you can't see a complete picture, right? Because your R is infinite. Okay, if you try to see in some finite domain, then certainly there will be some kind of problem. Okay, so here actually it's increasing. Okay, you by looking at a small picture, you may feel like, okay, this is flat. Okay, but it's increasing, because if x1 is greater than x2, okay, then x1 cube is always greater than x2 cube. Okay.
Okay, sir. Yes.
Yeah. So you may feel like this is so. For example, if you see the graph of x4, right? Let's say if you draw the graph of x4, okay, in this part, okay, only on the positive part, right? So you may feel like, okay, in this part this is flat. Okay, this is not flat. Okay, so this is increasing. Okay, if you see a small picture, then you may feel like, okay, in this part this is flat, but this is not flat, this is increasing.
Right, sir. Right, sir.
So the same thing is happening in x cube as well.
Excuse me, sir.
Sir,
then x square should be not neither increasing nor decreasing, sir.
Yes, x square is neither increasing nor decreasing. Yes.
Okay, sir.
Yeah.
Thanks.
Okay, so
if there's some constant adding in x square, then
it's depend like x, what you want to add.
Just like, sir, x square plus 2,
then what do you think?
It should be neither increasing nor decreasing.
Yes, see, the thing is, okay, if you add something with x squares, so what you will get? It will be a parabola, right?
Yes, sir.
So if you draw the graph of a parabola, okay, what you will get? You will get a figure like this, right?
Yes, sir.
So from here you can conclude, right? It's neither increasing nor decreasing, right? Either, see, if you consider any parabola, either graph will be of this form, or maybe some graph will be of this form, right?
Yes.
So if you consider the above one, it's also neither increasing nor decreasing, right?
Yes.
And here also, if you consider the below one, this is also neither increasing nor decreasing, right? Because for the below one, this is increasing in this part, right? In this negative part, it's increasing. In the positive part, it's decreasing.
Decreasing. Yes.
So that's
yes.
why this as a whole, this is neither increasing nor decreasing.
Sir, any expression like formulas or for finding increasing or decreasing?
No, there is no such formula. Okay, so for specific class of function, you can easily do it. Okay, otherwise it's not easy.
Okay.
Okay, so
Sir, but we can easily find out, right, by putting the values of, I mean, if we have a function, we can put the values of x1 and x2, and then we can monitor like how the function behaves, and that accordingly we can find whether it is increasing or decreasing, right?
no, you can. How you are going to do that? So see, the thing is, okay. See, for that you have to know the behavior of the function, right?
Yeah, if the function is given, then I'm saying, then we can find, right?
Again, it's depend how easy that given function is. Okay, so if you have a very complicated function, okay, it's really difficult for you to guess by putting some few values.
Then, sir, how to find if it is complicated?
And that is what I'm saying. It's in some cases it can be really complicated to know whether this.
But sir, in the exam, if the question comes with
No,
the function,
see the exam, whatever you are studying, they are very easy. Okay, so
in that situation, we can put the values and
yeah.
find.
So what basically you are studying? Mostly you are studying linear function, exponential function, some polynomial function. They are very easy to deal with. Okay. Yeah. So, but my point is these are not the only function. Okay, so there are huge lot of different functions. Okay.
Sir, hello.
Sir, you told that finding the derivative, if it is less than 0 and if it is greater than 0, we can conclude that it is increasing or decreasing function. So can you elaborate it, sir?
Okay, I'll come to that.
So take the e to the power of minus x or e to the power of x.
What do you mean by elaborate? Okay, what
means, sir, how we will find it is less than 0? If it is a quadratic equation, then the derivative will also a equation. So derivative can be positive or negative for some values of x.
Okay. Just give me a minute. Yeah. So suppose you have a function, right? Let's say a to b, right? And I'm assuming that f is differentiable. Otherwise, I can't talk about the derivative, right? So if I'll ask you, let's say, greatest integer function, you can't apply this derivative test because this is not, if I consider this function R to R.
Sir, it is also an increasing function, greatest integer function.
It's increasing function, but it's not strictly increasing function. Okay. But again, you can't apply the derivative test because this function is not differentiable. Okay. So, so suppose you consider a map from A to B, which is differentiable. Okay. What actually I'm saying, if f dash of x, right, is greater than 0 for all x in A, okay, then f is increasing on A, right? See, this increasing and decreasing, that depends on the domain, right? Which domain you are considering, right? For example, just now I said, right, if I will take this function, okay, whatever this function is, only on this part, right? On this part.
Okay, so basically we are finding, sir, that slope is always positive.
Correct. If the slope is always positive, then on that region the function is increasing. Okay. And the if the slope is
so if one function will be decreasing, then slope will be negative.
Yes.
Yeah.
Then f is
now I got it, sir.
So it's depend on the domain. Okay.
Sir, if we take f of x
but
is equal to
but in that domain, if there are multiple zeros, sir, if that in domain there are multiple zeros, then in that case it can be both increasing and decreasing.
Sorry?
In that domain, if there are multiple zeros of the graph, then it can be both.
You can't conclude anything. You have to check.
You cannot conclude. Yeah. Right.
Sir, I was asking if we take f of x is equal to e to the power of x, and if we differentiate, then also we can get similar.
Yeah.
E to the power of x or e to the power of minus x, both the cases.
So if you consider f of x equal to e power x, and if you take the derivative f dash of x, again this is e power x, right? And you know this is always greater than 0, right?
Yes.
So from here you can say that this is strictly increasing. Okay. Okay,
Yes.
this I should write f is strictly.
Hello, sir.
Just a minute.
Sir, when we call strictly increasing,
and if I consider e power minus x, what I will get? What is f dash of x?
minus
Minus e power x.
Which is always less than 0, right? That means this is strictly decreasing, right? Because the derivative is all strictly less than 0, so that's why it's strictly decreasing. Yeah. Any doubt so far?
Yes, sir. Sir.
Hmm.
So if the domain is all natural numbers and the parabola is right opening, then what will be the it will be increasing or decreasing, or both, or neither?
See, for the domain, when your domain is natural number, then see the problem is you can't use this test. Okay, so the domain should be some interval. Okay, it should be in the form of some interval. Okay, if you take bunch of discrete number, okay, then you can so there actually the concept of differentiability actually doesn't make much sense. Okay.
Okay.
See, if I consider this example, okay, let's say I have a function from 1, 2 to 2, 3. Okay. So the concept of derivative in this discrete set doesn't make any sense. Okay. So there is no point of you can't actually apply all this thing. Okay. So you must have some kind of continuous domain. So for example, this 1, 2, or maybe r, okay, or maybe -3 to 3. Okay, if you have a domain like this, then the definition of derivative makes sense here. Okay.
Okay, sir.
Yes.
So you can take domain R and the parabola will be right opening, then it will be what?
Sorry?
You said that we can take domain R. So the parabola will be right opening, then what it will be?
You try to do, right? See, even without thinking, you are basically saying you try to do on your own first. Okay. You first try to do on your own. So I said you the definition, right? See, if you see, the thing is what basically I'm saying, if you consider this parabola, okay, let's say f of x equal to x square, right? So if you take the derivative f dash of x, right, this is 2x. Right. So if I consider this part, only this part, 0 to infinity, right? 0 to infinity. In this part, this is always greater than 0, right?
Yeah.
So that's why, as you can see in this part, this is strictly increasing, right? And if you consider this part, minus infinity to 0, okay, open interval, in this part, this is strictly decreasing, right? Strictly less than 0, right? So that's why in this part, it's strictly decreasing. You take similarly, you take different parabola, you can check, right, in which part it's increasing, in which part it's decreasing. Again, as I said, see, if I consider from R to R, okay, if I consider this function from R to R, then I can't say that my f dash of x is greater than 0 for all x in R, right? I can't say that. Right? So I can't conclude anything. But if I consider only from positive real to positive real number to R, in that case, I can say that my derivative is strictly greater than 0. In that case, the function is infinite. Okay. Okay. So next thing I want to discuss is composite function. Okay. Okay, so yeah, again, like you basically know how you can find the composite function. The only reason I want to discuss this composite function because I want to define inverse function.
Sir, in composite function, can you please take the example of mod functions?
Yeah, I can take, but okay, just let me know which examples you want.
Sir, I don't have that example readily available, but I will look for it.
Yeah, so yes, you take your time. I maybe you take 1 minute or 2 minutes if you have something on your mind, just keep. Yeah, so okay, so basically so main idea is you want to compose two functions, right? So what basically you want to do, suppose you have a function f from A to B, and what G from C to T, right? So what I want to compose these two functions. Okay. So when I can compose, so as you can see, so I have this G, and this is the domain, right? And it's going, this is something, it's going to this thing. Okay, this is my F, and this is the codomain of F. So I can talk about this composition. Okay, I can talk about this composite function when this G land inside the domain of F, right? See, if G doesn't land inside the domain of A, then this F of G of X doesn't make any sense, right? So I have to make sure that this G always land inside the domain of X, right? So we are assuming that this G is whatever value G is taking, it's always inside the domain of F of X. For example, see, if I consider this map, let's say if I this is, let's say, R to R, not R to R, R minus 1, right? So this is 1 goes to, not 1, X goes to 1 by X minus 1. Okay, and my G of X is also a map from R to R. So if I consider this F compose G, then if I so the domain of G is basically R. So if I take this one, if I evaluate this composition function at 1, then what I will get? F of G of 1, right? And now what I'm getting F of 1. So now I'm in trouble because this 1, I'm getting 1 here, and 1 is not inside this domain. Okay, so again, like certainly we can avoid this situation. Okay, but you have to always make sure that whatever G you are considering, the value of this G should always inside this domain of this function. Okay. Yeah, so let me take few examples. Any example you want me to?
Sir, can I share the question from the previous year? Actually, this one was discussed, but I still want to understand.
Yeah, tell me the question.
So
I can't. allow you to share probably because I'm not the host of this. I have to ask someone else.
Sir, I can read out if you want.
Yeah, tell me. Yeah.
So let f be a function whose domain is close interval -5, 7. If g of x is equal to mod of 2x plus 5
G of x
is equal to mod of 2x plus 5 and a comma b, close interval a comma b denotes the largest interval which can be a domain for the composite function. The composite function is f of g of x.
Right, this one.
Then find the value of a plus b.
Correct. Okay, so as you can see, as I said, when you can define this composition. Okay, so this composition makes sense. Okay, so the domain, it's already given that f is a function from -5, 7 -5, 7. Okay, so this is the domain of it, right?
Yeah.
Then this composition, what is this composition? This is precisely f of g of x, right? So this f of g of x makes sense when g of x is inside the domain of f, right?
Yeah.
That means this definition makes sense when 2x plus 7 modulus, sorry, 2x plus 5 modulus is inside where?
F.
In the domain of f.
-5 to 7.
Correct. -5 to 7, right? Yes. Yeah. So this 2x.
What is A and B in the question, sir?
Domain of GF.
So you need to find the domain of this composite function. Okay, f comma g. Okay. So basically, what you are trying to find? You are trying to find all such x, right? All such x in the real line, right? For which f compose g of x makes sense, right? So when this thing makes sense, when this thing makes sense, right? And when this thing makes sense, when g of x is inside the domain of f, right? So basically, what do we need to find? We need to find all such x for which 2x plus 5 modulus is less than or equal to 7, greater than or equal to -5, right?
Yes, sir.
So from here, what you can do? Any idea?
Sir, we will take two cases in this, like one positive and one negative, and then we'll solve.
Yeah. So if you take the positive one, what will happen?
Sir, we will, the left side become -10.
-10.
Yeah, because it will go, right? 5 will go to the left side.
No.
No?
It's -1.
Mod also break into two parts, no?
Mod, yes, sir.
Yeah, that's what I'm saying. It will, the two cases will be there, 2x plus 5, it's a positive case, and another case when it is negative.
0 less than
Right?
equal to.
So this is one case, right?
Yeah.
Yes, sir.
This is one case. And what you can get if you add 5 on both the sides, what you will get?
0 less than
0
less than equal to.
Oh, we have to do like this. I was okay.
12, right?
Okay.
Correct?
Yes,
I mean, yeah, just let me know if I'm
-5.
Minus 5.
Sir, it will be 2x plus 10. No?
-10.
Correct.
Oh, so I was correct, right?
Yeah.
Okay.
Yeah, so basically I'm making mistake. So what you have to do, you have to basically add -5 because I want to cancel this. Okay, so if I
Yes.
cancel this, then I will get -10
less than equal
2x.
less than equal to 2x.
This is 2, right?
2.
Yes, sir, 2.
So that means x is
-5 to 1.
right.
Yes, sir. So for this, we have got one interval.
So what is the next case?
We have to take a case for negative. So -2x -5.
No, tell me the initial part. Okay, 2x plus 7 is less than.
Sir, it will be like we have to change the equation, the inside equation, right?
Yeah, that is what I'm saying. You are saying
-7.
-7.
Yeah, so okay, so yeah, you are correct. Whatever you said, you are correct. So if you take the -1, then actually you have to multiply a -1. Okay, so in that case, you will get this sign.
+5.
If I multiply, then I will get -7. Yeah, so this is what I will get.
Equality
No,
change.
no. Yeah, equality will change. So
Sir, it will be less than 5.
So okay, so let me write this. You will get, right?
Yeah.
Correct.
Yeah.
Yes, sir.
So this is minus. This is -2x plus sorry, -5.
-5. Less
Sir,
than
if we remove the negative signs, then it will be there will be no solution for this.
Yeah. So eventually you will get the no solution. Yeah, that is what I'm
Because
trying.
nothing can be greater than -5 and
Minus
less,
nothing can be
greater than -5 and greater than 5 and less than -7.
Yes. So now what you will do?
Equality change.
Add 5.
Sorry?
Adding 5.
Adding 5. What you will get? Here you will get 0, right?
0.
-2x.
12.
Yeah.
12.
And from here, what you can get?
Then we will divide to -2.
Zero.
At
It
this,
will be 0.
This is
we have to change the equality sign now, right?
which one?
Sir, don't we have to change the equality sign?
Yeah, correct. So now if I multiply my -1/2, then what I will get? I'll basically get this is -6, right?
Yes, sir.
Which is greater than
X.
which is less than
0.
Correct. Okay. So so finally, what I'm getting? Any idea?
We have got two intervals and
X
now
belongs to -5 to
-6 to
1, right? And here what we are getting?
-6 to 0.
-6 to 0.
And if I take the union, what I will get?
Sir, how we got this? Because if we go through the first line of the second case, so nothing can be less than less than 5 and greater than what we got.
Am I making any mistake here?
no, sir. I think it's correct.
These are asking it out.
No, sir.
So what is the answer of that question? Do you know?
Yeah, 5. -5.
-6 to 1. The
What is
-4, I think it should be.
no -5.
No, -5.
If we take union, then it will be.
so whoever asked this question, can you tell me the answer of this question?
Sir, I don't
Sir,
remember,
still
but
it's
I
A
think
plus
many
B is
people
equal
have
to
attended.
Sir, -5.
Okay,
Must be -5, yes.
so if I take the union, okay.
Yeah, -5, yes.
So
It
see,
become -6 to 1.
so if I take the union, what I will get? -6 to 1, right? And yeah, so if this is matching with the answer, then probably I will not
Yes,
take.
sir. Now they have asked A plus B, so we simply have to add this
Yeah,
minus
yeah,
6
so
plus 1. It will be -5.
5,
Thank
yeah.
you.
Yeah, if it is
Sir,
matching.
how you changed this
but,
sign and
if
the
G's
equality sign?
domain is -5 to 7, then how come it can go further than that? I mean, -6 is beyond -5's domain. I mean, how can it be happen, sir?
Sorry.
So G's domain is FA's domain is -5 to 7, no, sir. Then how can it go further? I mean, beyond that domain.
Okay, I'll suggest you try to revise, go through the lectures. Okay, so see, the thing is how you define F compose. Okay, what basically in the question it's asking? Why in question what is asking? What is the maximum possible interval? Okay, maximum possible interval in which this F compose G is defined, right? So if I see, if I have a function 1 to R, right? And if I have a function S goes to 1, right? So if I talk about F compose G, right? Then this basically makes sense for all X inside R, right? Because see, if I take G of X, it's always 1, right? And 1 is already there in the domain of F. So I can compose, right?
Yes, sir.
Yeah. Okay, so yeah.
Yes.
So in the question, actually, it's asking for what is the maximum possible interval. Okay, what is the maximal possible interval for which this composition makes sense. Okay. Okay, so yeah, so let me go to where the inverse of a function. Okay, so what is the definition of inverse function?
Sorry, it's only one function that can be converted into inverse.
Correct. So suppose I have a map A to B, which is 1, 1. Then I can say, so then actually I can talk about the inverse of this function. So then the inverse of this function, F inverse, is a map from where to where?
B to A.
B to A, sir.
Not B to A, actually. Yeah, so if I assume that this is also on to, right? Then I can say that this function is from B to A. Okay. So otherwise, okay. So let's say this function is 1, 1 as well as on to, right? Then F inverse is a map from B to A such that it satisfies these two conditions, right? F compose F inverse of X is X and F inverse compose F of X is also X, right?
Yes,
See,
sir.
what is the reason why actually I assume this onto, right? Only because I can write here B. Otherwise, instead of B, I have to write range of F, right? See, you know, right? The domain of F inverse is basically the range
of F. Yeah.
range of F, right? So if you want to write B here, okay, then basically you are basically saying this F is surjective, right? So then only you can write here B, right? Otherwise, instead of B, you have to replace B as range of F, okay. And and similarly, the what domain of F is equals to the range of F inverse, right? Correct. And one more thing, most of the time, like most of you do this sort of mistake. So there is a difference. Okay, so this F inverse F X is not equal to 1 by X. Okay, so these two things are different. Okay, so don't treat them equal. Okay. So for example, if you consider F of X equal to X, right? If you consider F of X equal to X, this is what? This is a 1-1 function from R to R.
Yeah.
This is 1-1, right?
Yeah.
What is the inverse of this function?
Same function.
Sorry?
Same X.
Yeah, this is the identity function, right? So F inverse of X is also X, but certainly this is not equal to 1 by X, right?
Yeah.
So they are two different things. Okay. Okay, so okay, let me take few examples. So you consider this function F of X equals to 3x minus 5, right? You consider this map from R to R. What about this function? Do you think this is a 1-1 function?
Yeah, 1-1 function.
Right? This is 1-1 function. What is the range of this function?
All
Real numbers.
Yeah,
except
this is a line, right?
Yeah.
So the domain is whole real, right?
Yeah.
Sorry, not domain. The range is whole real, right? So if I consider the F inverse, then this will give me a map from R to R, right? And how I can find the inverse of this function?
Assuming gx is equal to y.
Correct. So let's say what?
so it will be y plus 5 upon
y,
10.
sir.
Yeah, let's say this is the inverse, right? G is equal to F inverse. Then you know F compose G of X is what?
G of F of G of X.
Yeah, this is X, right?
Yes, X.
That means F of G of X is X. Okay. So now you just represent this G of X as Y, right?
Yeah.
So your F of Y equal to X. That means what?
3y minus 5
3y
equal to X.
3y minus 5
Is equal to X.
X, right? That means your Y equal to
X plus 5 by 3.
3. Right. So that means your G of X is equals to X plus 5 by, right? So So yeah. So as you can see, this is the inverse of this function. Okay, and similarly, like
So we have to take the opposite also, g of fx.
Yeah, g of f of x also you will get. So again, if you do, you will get the same thing. Okay, so what the last thing what you need to check whether they are satisfying this condition. Okay, this see if you instead of checking that, if you can check that with whether this function is satisfying this condition, okay, then also you are done. Okay, you don't have to check that one. Okay, see, the only thing what you need to check, you need to check you have a function which satisfies these two conditions, right?
Yeah.
So here, as you can see, what basically we have done, we in some sense we basically showed that this f compose g is x, right? And from by equating this, we are getting g to be this one, right? And next, if we can show that g compose f of x is x, then we are done. Okay, so you simply take this function and you check whether this function is satisfying this condition. And you can check that this function will satisfy the condition. That means this is the inverse of the given function. Okay, so okay, so let's say okay, so if I consider this function, R to R, what about this one?
This is not 1, 1.
This is not
1-to-1 function.
Yeah, this is not 1, 1, right?
So the inverse will not exist.
So
right?
then, yeah, then this function has no inverse, right? Just give me a minute. Someone is asking something in the chat box. Okay. Okay, so this is not, so since this function is not 1, 1 function from R to R, then I can't talk about its inverse. Okay, at least in this given domain, right? So next you consider this function. Let's say f of x two. So can you tell me the domain of this function?
Yes, so -2/3.
-2/3, correct.
R 2/3.
So -2/3 to, let's say, R, right?
Yeah.
So this is the domain. So do you think this function is injective?
Yeah.
Why?
It pass horizontal line test, I think.
Sorry?
It pass horizontal line test.
What is the graph of this function? If this function passes horizontal line test, then you must have the graph of the function. Tell me what will be the graph of this function?
I think it will be increasing like so.
Okay, it's also, you can see very quickly. I really don't see how this will become increasing. Yeah.
So we can also take a negative -1 and 1, and then we will see. This will give a different output, so it will be 1-to-1.
This is certainly 1-to-1. Okay, but again, like you it's better, like it's easily you can prove that this function is actually 1-to-1. Okay.
By the same way, sir, when we were discussing Like we take x1 and x2 and then put value, both will be equal. And then solving the equation, we will get x1 is equal to x2. Yeah.
So let's say f of x equal to f of y, right? And okay, so your task is to find the range of it. Okay, that you need to find. Okay, this you need to find what is the range of f of x. I am not going to find the range of this function. Yeah, I can't. I don't think I can finish by 8. If you want to leave, you can leave. Later you can watch the recorded. So and what is this? 3y plus 1, 3y plus 2, right? So next what you can do, you can cross multiply. Okay. If you cross multiply and after that, if you if you simplify, you can actually show that x is equals to y. Okay. It's easy. Okay. So again, so what we need to do, we need to find the inverse of this function. Okay, so let's say the range of this function is, let's say, d. Okay, as far as I know, the range of this function is not whole r. Okay, most likely it will miss one point.
It will be 3 by 2.
So you were saying it will miss 3 by 2.
Yes, sir.
No, I don't think it will miss 3 by 2. I think it will miss something else. So you try to check. Okay. So so f inverse is a map. Let's say the range of f of x is d. Then it will be a map from d to where?
Excuse me, sir.
Yes.
How did we decide this is 1, 1? I didn't get that part.
So so what actually I am trying to prove, if f of x is equals to f of y, then I am trying to prove that x equal to y, right? So so now you try to, so from f of x equal to f of y, you will get this thing, right? Now you try to simplify this term. You multiply this one with this one, right? And so if you multiply, what you will get? 3x plus 1 times 3y plus 2 is same as 3y plus 1 times 3x plus 2. Okay, now you try to simplify it. Okay, you will get x equal to y. Okay, you try to SCG. So then f inverse is a map from d to r minus where? Minus 2 by 3, right? And then how you are going to compute the inverse?
By the same way, sir, considering gx is equal to y.
Right? This is x. That means what? F of g of x equal to x.
Yes.
That means f of, I'm considering this equal to y, f of y is equal to x, right?
X.
And what I will get, f of y is what? Y plus 1 divided by 3y
plus 2,
which is x, right?
X. Yeah.
Now if I cross multiply, what I will get? 3y plus 2 is y plus 1, and this is nothing but 3yx plus 2x is equals to y plus 1, right? And this will imply what?
3yx minus y is equal to?
Minus y
is equal to 1 minus 2x.
2x And that
Then we'll
means
take y common.
correct. 3x minus
3x
1.
minus 1.
Mhm. So, so y equal to what?
1 minus 2x
minus 2x
upon 3x minus
3x
1.
minus 3
3x minus
Minus
1.
1.
1
Right?
right.
So, so this is, so what is this? This is d of x, right? And you can check actually, this is the inverse of this function. Right?
Yes, sir.
Now you tell me what is the domain of g of x?
1 by 3. All real lines.
Except 1 by 3, right?
Yes, sir.
So this is precisely the
A range of that.
yes. Right. So I asked
Yes,
you,
sir.
right? What is the range of this, right?
Yes, sir.
So once you have this g of x, is from here itself you can say what is the range of this. Okay. Okay. So okay, I spent a lot of time here. Okay, so let me move to this
Exponential map.
yeah. So yeah, so exponential map. Okay, so
Sir, what do we mean by exponential map?
it's basically it's a map of this form. Okay, where what is the condition on a
is greater than 0 and not equal to 1.
and a is not equal to. So if you have a map which is of this form, then you say that this is precisely exponential map, right? And the nature of this map depends on the values of a, right? So you know if a is in between this range, right? This map behaves slightly from the range when a belongs to this interval, right? So if I draw the graph of this function,
Decreasing graph it will be. Asymptote to y. Right, sir?
asymptote to
Y-axis.
no, in both the cases it will be asymptote to x-axis only.
But in this condition, it will be decreasing.
Yeah, I agree this is decreasing, but certainly it's not asymptote to y-axis. See, this will be the graph of this, right?
Oh, okay, okay.
Right? So, and in this case, if you draw what will be the graph?
Increasing graph
Right.
it will be.
Increasing, right? So as you can see,
Excuse me, sir. In the second graph, sir, a belongs to 1 to infinity. Then, sir, this graph is cut to y-axis at 2.1.
0, 1.
Yes, 0, 1. So this is first and second. Okay, sir.
This is
0.02.
this is also 0, 1. Okay.
Okay, sir. Okay, sir. Fine,
So so there are few things that, so as you can see, when you are moving, so for this case, when you are moving along this x-axis from this negative part to positive part, then the value of this function is decreasing, right? And so this is behaving slightly different. So when you are moving along this x-axis, this is
increasing,
right? So as you can see, so there are few things to see here. So in both the cases, the domain is what? In both the cases, the domain is what?
Real line.
Real line, right? So in both the cases, the domain is real line. And what about the range of this function?
They will be, sir, real.
Range?
0 to infinity.
0 to infinite, right, sir?
0 to infinite. 0
Yes,
excluded, right?
Yes, sir,
Yeah.
yes, sir.
Because it never touches the x-axis, right? So 0 excluded, right?
Yes, sir.
And because, and also this is always above the x-axis, right? So that means the value is positive. That is precisely, it's basically means, yeah. So from here, you can say that the value of the function is always positive, right? And the next thing is, as I said already, there are no x-intercept, right?
Yes, sir.
And the y-intercept is 0,
0, 1.
1, right? And
Yeah.
for both the cases, y equal to 0, that is x-axis is a horizontal
asymptote.
Yes.
Yeah, horizontal.
And yeah, and one more thing, probably, yeah. So again, this function is 1
to 1 function.
and this part is actually this part is decreasing, or you can say that strictly decreasing, and this part is strictly
Increasing.
increasing, right? And so this is more about this exponential function, and as you know, this function is 1 to 1, right? This function doesn't matter what the value of a is. Of course, a is we have two possible cases of ax. So this function is always 1 to 1, right? From where? From R to 0,
0 to infinity.
right? So then, yeah.
Sir, I am unable to understand one-to-one function, sir.
Unable to understand 1 to 1 function.
Yes, sir.
For why this is 1 to 1, or in general, what is 1 to 1? Sorry?
Yes, sir. Yes, sir. Yes, sir. Difference between 1-1 and 1-to-1 function.
No, they are same. 1 to 1 and 1-1 basically same. Yeah. So
okay, sir.
They are same. 1-1. Okay.
Okay,
So
sir,
you understand 1-1 function, right? They're
Yes,
basically same. Yes. So
Yes.
yeah. So it's just a notation. Okay. So sometimes some writes 1 to 1, and you can write this as 1-1. So this is a 1-1 function. So once this is a 1-1 function, then what I can do, I can talk about the
Inverse.
Inverse, right?
Yes, sir.
And what is the inverse of this function? What is the
Log to the
Logarithm.
base a x.
So the inverse function is what? This is the log base a. And what will be the domain of this function?
0 to infinity.
Yeah, because the range of this function is 0 to infinity. And what will be the code? What will be the range of this function? Log function, it will be whole
Real number, real line.
Real line.
right? So this takes x2 log a x, right? And by the definition of logarithm, okay, by definition of the logarithm, you can say that this log a x equal to y, right? If and only if a power y is equals to
X.
x, right? again, let me tell you, this is one of the most important thing in logarithm. If you know how to use it properly, then you can solve almost all the questions. Okay, so and why actually this property is coming because of this relation, that log is a inverse of your exponent. Okay, so yeah, so let me go to next page. And yeah, so the log, again, similarly, since this A has two set of range, okay, similarly, when I'm defining this log of X, okay, this X has also two set of range, right? A is and 1 to infinite. And we are excluding 1 for obvious reason, right? And now can you tell me what will be the graph of this logarithm?
Vertical asymptote.
What will be the graph?
Vertical asymptote, sir.
When A is in this region. Vertical asymptote is not an answer. I'm asking what will be the graph. You are basically saying vertical asymptote. What basically this means?
Decreasing, sir. Decreasing graph.
Yeah. So this will like this, right? And what is this point?
1, 0.
Correct. See, because as you can see here, I have 0, 1, right? Here I have 0, 1, right?
Yes, sir.
So if I take the inverse, then I will get basically what? It will be a reflection with respect to this axis, right? With respect to this line, right? So in that case, I will get this graph. Okay. So that's why. So the reflection of 0, 1 with respect to 1 by x, with respect to y equal to x line is basically 1, 0. Okay. And again here you can say that this function is decreasing, right? When you are moving in the positive direction of this x-axis, the value of the function is coming down and down. Okay, so this is a increasing function, and similarly you can say that this is also 1, 1 function. Okay, because your exponential itself is a 1, 1 function. Okay, if f is a 1, 1 function, then the inverse of the function is also a 1, 1 function. And what will be the graph of this one when a is in between?
Increasing graph.
Increasing.
Okay, so this will be something like this, right? So this is an increasing graph, and this point again
1, 0.
And as you can see, if you move, this basically increases. So if you try to compare the property, then what is the obvious thing you need to change? Again, see the domain
and range.
Okay, so the domain and range will get reversed, right? And
Yes,
so here there is no y-intercept. Okay, here you have only x-intercept, right? Correct or not? This is the only x-intercept, right? And
yes, sir.
Yeah. So and similarly you have the asymptote, right? So here x equal to 0 is asymptote, right?
So here x will always be positive, no, sir?
Yeah. So here domain, the domain and range will reverse, right? So here the domain is what? R, right? So for logarithm function, it will be the range of the function, right? So if you consider log basically what? R is the range, right? Or you can say as well as codomain. And if you consider here, the range is 0, infinity, right? And in this case, the range is the domain is 0, infinity. So it will get reversed. So now, okay, let me solve few questions. Okay, let me start with the the domain, how to compute the domain of some logarithm. Okay, not this one, some slightly modification of a logarithm. Okay. So if you consider this function, let's say what will be the domain of this function? What will be the domain of this?
Infinity. Real number, sir.
Real number. Why?
2 to infinity, I think.
X square minus 3 should be greater than 0.
Correct. See, what is the domain of log x?
0 to infinity.
What is the domain of log x? This is basically 0 to infinity, right? Domain of this is 0 to infinity. Right? So instead of x, what you have? You have x square minus 3, right? So then what you want? You to show that this expression makes sense, you want your x square minus 3. So you have to find all the possible values of x for which x square minus 3 is greater than 0.
0.
Right?
Yes, sir.
So, sir, the base is not affecting the domain. If it is less than 1 or...
But you can see, right, for both the cases, it doesn't matter, right? Its domain is always this part, right? If you see the graph in both the cases, the domain is this part, right? Because here the base doesn't matter what a you are taking. Okay, your range is always same. It's basically 0 to infinity. So that's why here also base doesn't matter. Okay.
Okay, sir.
So you want this x square minus 3 to be greater than 0. That means you want what you want? X square to be greater than 3. Then what will be the range? Hey, what will be the range of this x? If x square is greater than 3, what will be the range? X is right?
Yes.
So this is your domain, right? Domain of F. Any doubt?
No, sir.
No, sir.
Okay.
Sir, sometimes base is also given as variable. Then at that time, what should we do?
Yes, so it's depend which question you are talking.
Take care of both.
Take
Base
one
and
example.
Yeah,
of
see, so see when base is given, so yeah, so you have to make sure that this base is not equal to 1, right? As well as it should inside this range, right?
Okay.
Okay, so let's take one more example. Yeah. Any idea how should I solve this question?
Yes, sir. This can be
Division.
by
We can bring it to the as minus.
ln of 2x plus 3 minus ln of x square minus 9. Then simplify.
The entire real line except 3 and -3.
How? Can you tell me how you are getting this?
Sir, we are checking this 2x plus 3 upon x square minus 9 is a part of real number or not.
Should be greater
Sorry,
than
sorry. It is to be positive also.
be greater than 0. Not equal.
Yeah. Yeah,
It
so
should be greater than -3/2 and plus -3.
So what we need to make sure? We need to make sure that this part is greater than 0, right?
Right.
So that means 2x plus 3 divided by x square minus 1 should be greater than 0, right?
Yes, sir.
So then what is the next step?
So x is greater than 3.
2x plus 3.
Shift the denominator to the other side, sir. Then it will become 0.
We can't shift directly in inequality.
See, you must have solved this type of question in your activity, right?
Yes, sir.
Yeah. How you solve that part?
Multiply by x square plus 9 both.
So
Divide by x square plus.
This is what? 2x plus 3 times. Please mute yourself. Right?
Yes, sir.
Raj Deepak, can you mute yourself?
Sir, we have to separate.
Am I audible?
Yes, sir, you are.
Yes,
Yes,
sir.
Yes.
Okay, so now this is, you can think of this as A, you can think of as B, right? So what I'm saying, basically A times B is greater than 0. So when this is possible? When A times B is greater than 0?
Means both
are positive.
A and B should be greater than 0, sir.
Both are negative.
Right? This is one case. And this is
Both
are less than 0
also. Positive or both are negative.
yeah. So that is what I have taken two cases, right? One is this one, another one is this one. And right?
Yes, sir.
Yeah. So
sir, here, sir, B should be also greater than 0, no?
you read what I have written. You try to read
Yes,
what I have.
understand.
0 and x square minus should be greater than 0. This should hold simultaneously, right? So that means this is x is greater than what?
-3/2.
Right?
Yes, sir.
Yes.
That means x should be in between this interval. -3/2 to infinity, right?
Yes, sir.
And here, what is the range? X is in between
3, 2.
minus infinity
Three.
to root 3
2, 3, yes, sir.
union. Sorry, minus root 3 minus plus root 3 to infinity. But what do we want? We want both the things to be whole simultaneously, right? For that, we have to take the what? Common part, right? So what is the common part? Sorry, this should be not -3, this should be 3.
Yes, sir.
What is the common part? See, we want this to be greater than 0 as well as this to be greater than 0, right? This is greater than 0 in this region, right?
Yes, sir.
And this is greater than 0 in this region. Okay, but what I want both of them to be greater than 0. And when this is possible, when I have to, when I have
-3 by 2 to -3.
when I take the common region, okay, which is the common region to both the region. The region is precisely 3 to infinity.
3 to infinity.
Yeah. Okay, so the next part is this one, 2x plus 3 is less than 0 and x square minus 9 is less than 0, right? And this is less than 0 when x is less than -3 by 2, right? Minus infinity to -3 by 2, right? And this, what is this region? This is -3 to 3, right? And again, I want both the things to hold simultaneously. For that, I have to take the common region. So what is the common region?
-3 to -3 by 2.
Correct. -3 to -3 by 2. Okay. So that means the domain of this function is nothing but 3 to infinity, okay, union -3 -3. Okay, or like, yeah, it's better to write the other. Okay, any doubt?
No, sir. No, sir.
Okay, fine. Okay, so then probably, yeah, I'll stop now. Because
What about calculus part?
Calculus, there is one more session. There is one more revision.
Okay,
Don't worry about calculus.
When we are planning that, sir?
It's already in the calendar, right? 31st, right?
Oh, okay.
You can check in the calendar. It's in 31st. 31st
Every morning.
Yeah. Okay.
Thank you, sir.
Yeah, thanks.
Excuse me, sir.
Thank you, sir.
Yes.
Yes, sir. What is the syllabus for sir quiz 2 of mathematics?
Quiz 2 mathematics.
Yes, sir, syllabus.
1 to 8.
See, all the question will come from 5 to 8. Okay.
Yes, sir.
But the thing is, even to solve the questions of 5 to 8, you need the concept of week
1 to 8.
1 to 4.
4, yes, sir.
So again, we will not ask you any direct question from week 1 to 4. Okay. Whatever question we'll ask, mostly it will be from week 1 to 5 to 8, but still you need the concept of week 1 to 4, because see, week 1 is also 1 1 1 2 function, right? So yeah, so some kind of overlap is there, right? So,
Yes, sir. I have confused about sir sum of square error.
don't worry about some square.
SSC, sir, mathematics.
At least for quiz 2, okay. But you have to worry about some square error when you will give n terms.
Sir, can I ask you one question? Sir, I want to ask, like, difficulty level of the quiz 2 will be higher than quiz 1, or it will be same?
That I don't know.
So higher than mock or as same as mock level will be?
See, quiz 2 question is easy, okay, as far as I can see. Okay,
So it will be easier as per to quiz 1. We
again,
cannot say.
No, for that
Or
I
you
have
may,
to.
or maybe you cannot compare.
I have to go and check the quiz 1 question. Okay, I remember quiz 2 question. I don't remember quiz 1 question. Okay. So see, quiz 1 question. Okay, it's more or less easy. The only thing I can say that it's easy. Okay, the calculus part is really easy. Okay.
So it will be easy or difficult calculus part, what you said?
Calculus part is much more easier than the other part.
Okay.
This week 7 and 8, okay, questions from week and 7 and 8 are much more easier than the question of week 5 and 6. If you know the concept, like the definition and some example very well, okay, you can solve all the questions of calculus.
Yeah, this is what, sir, I have seen up till now. If you know the concept, then you can solve It's not the formula based. If we learn the formula and go, then we cannot do. We really need
you
concepts.
don't, okay. So
The
you don't,
questions I never seen like,
you don't have to remember a single formula. Okay.
yeah.
Sir,
Of course,
derivatives
the obvious one, like the derivative of sin x. Okay.
Yeah,
The
yeah, of
derivative
course.
of cos x. That you have to remember. Okay. You can't expect all the things in your example. Okay. Apart from some obvious formula, you don't have to remember anything. Okay.
So a few questions from the previous paper, I really find it difficult.
Yeah, correct.
A few questions are really difficult.
Yeah, but fortunately,
able to solve.
fortunately, in this term, you don't have this type of. Okay.
Have you said the paper of quiz 2?
No, I didn't say it.
Okay, sir.
But again, I have seen the question. Okay, I'm not just simply saying everything. Yeah, Subham actually prepared quiz 2 paper. Okay, so yeah, so as I said, like week 5 and 6 are slightly whatever I felt. Okay, it's not that it's not a uniform opinion, but whatever I felt, I feel like yeah, calculus part is much more easier than your this week 5 and 6 part, because I don't see any complicated question in calculus. It's mostly straightforward. Like by just looking at the question, you can solve all the questions. Okay, you don't have to use pen and paper. Okay. But again, you should know the concept very well. Otherwise, again, if you don't know the definition properly, you don't know, then certainly you can't do it. At least try to understand the definition properly. Okay. Then at least you can solve for the calculus part. You can solve most of the questions. Okay, but yeah, but week 5 and 6 are slightly difficult. You have to know the concept very well.
So the question will be completely different or similar to mock
That
grading.
I don't.
Okay.
I gave you enough information. I can't share much. Okay. Yeah. So yeah, I'll stop now.
Right.